presents Parts Inspection, the key to failure analysis. Thorough inspection of failed or damaged parts is the key to an effective failure analysis program. But the parts alone can't give you the whole picture. You must develop the habit of checking the vehicle's history, along with information about the age of the transmission and the care it has received. Gather information about its maintenance schedule, driving conditions, and past failures or problems. Look for answers to questions such as, has the proper type of oil been used and has it been changed regularly? Is this a repeat failure which wasn't analyzed correctly the first time? Is there a history of driver-related problems? Or has this unit lived out its expected life? Combine these procedures with the information presented in this program and your experience to develop a thorough failure analysis and corrective action program for Fuller transmissions. Gears are the main components of transmissions. So let's start by examining gear failures and their causes. All gears wear as a transmission operates. Normal gear life is a constant and slow wearing of the gear tooth, hub, and spline surfaces. The rate of wear will vary depending on the torque of the engine, weight of the load, and other conditions, such as temperature and lubricant. Any gear can fail once it has exceeded its expected life. Adverse conditions can shorten their expected life, causing them to fail prematurely. The actual breaking of a tooth is a serious failure. Not only will the broken gear fail, but serious damage may occur to the other gearing as a result of the broken tooth running through the gear mesh. Fatigue fractures are identified by beach marks on the fractured area. These marks are made as the tooth progressively cracks under a load that is heavy enough to enlarge the crack, but not great enough to break the entire tooth off at one time. Fatigue fractures are caused by extremely high stresses on a gear tooth over a period of time. Possible causes of such stresses could be shock loads causing a small crack in the tooth, an overload condition, severe pitting, or surface fatigue. Impact fractures are identified by a bump on the fracture area and the absence of beach marks. The more cycles the gear has run after the fracture, the smaller the bump will be. Impact fractures are caused by a severe shock load, a heavy overload, or a foreign object passing through the gear mesh. Fractures are also caused by imperfections in the gear itself. Gears made from base metal containing gas pockets called inclusions or stringers will have weak points at those areas. These fractures can be identified by the difference in the fracture shape and metal texture in the brake surface. Remember, as with all fractures, inspect the transmission's gearing, bearings, shafts, keys and keyways, and case for possible damage. Gears can also crack across their hubs without pieces of the gear breaking loose. This type of fracture usually occurs on gears which are pressed on shafts, such as the countershaft assemblies. Often, cracked hubs show up as a knocking noise at low RPM or a howling noise at high RPM. Cracked hubs are usually caused by shock load or by improper pressing of the gear onto the shaft. Scoring and galling can be found any place where two machined surfaces are working against each other. High temperatures are produced as the surfaces slide over each other, causing the metal to soften. The softened metal is then smeared across the surface. Also, look for scoring on machined faces of gear hubs and on main shaft washers and spacers. The advanced stage of scoring, in which large areas of metal have been softened and smeared across the surface, is referred to as galling. Scoring is caused by insufficient oil film between mating surfaces, resulting in very high surface temperature. This results in an alternate welding and tearing of metal from the surface. Insufficient oil film can be caused by low oil levels, excessive transmission operating angles, high operating temperatures, poor quality or incorrect viscosity oil, and mixing types of oil. Detailed information on recommended lubricants can be found in the Lubrication Recommendation Pamphlet, Form 121, and the General Troubleshooting Guide, Form 102. Be sure to correct the lubrication problem, or it will come back to haunt you. Check the gear hubs and washers for wear. The washers are available in assorted thicknesses, which can be used to adjust the axial clearance between the mating gear hubs. Check the service manual for the correct procedure. Generally, proper adjustment is when there is 5 to 12 thousandths clearance between mating gear hubs. Excessive clearance between mating mainshaft gears will allow them to wobble, resulting in noise, scoring, and washer breakage. Frosting usually occurs as a line across the tooth face on only a few teeth. As the teeth drive against each other, minute particles of metal leave the tooth surfaces and produce a satiny or matte-like finish. Frosting can be simply described as microscopic pitting. All gears frost at one time or another during their lives, so don't replace gears simply because they are frosted. But if a gear is frosted and also shows signs of tip loading, misalignment, flat spots, pits, or other abnormalities, then replace it. Gear pitting is a surface condition which is normal in the early life of transmission. It is the result of microscopic variations in the tooth form. The pit size will vary depending on the depth of the initial fracture. Initial pitting is the mildest stage of pitting. Generally, initial pitting continues until the tooth is able to carry the load without further distress. In many cases, it will heal over. This gear shows pit craters approximately twice the size of the craters in initial pitting. The pits are widely distributed across the face of the tooth. The teeth have not been significantly weakened at this stage, and there is no danger of breakage. This type of moderate pitting will not cause noise. This gear can give many more miles of useful service. The pitting on this gear is well advanced into a destructive stage. The pit craters are larger and deeper. The gears and mating gears should be replaced. Spalling is similar in appearance to destructive pitting, but craters are larger in diameter and shallower in depth. Spalling occurs over a short period of time when a gear is subject to an extreme overload condition. Gears in this condition should be replaced. Operating a transmission with low or excessively high oil levels will cause it to overheat. When inspecting a transmission with a burned headset, it is not unusual to find the main drive gear badly scored with only slight visible damage to the mating countershaft drive gears. This occurs because the teeth of the main drive gear make contact almost 3 times as often as the teeth of the mating countershaft gears. When replacing a burned main drive gear, also replace the countershaft drive gears. Excessively high temperatures will draw the heat treat from the parts and eventually weaken them. Weakened parts will ultimately pit, score, and fracture. An easy check for loss of heat treat is to run a mill file across the surface of the part. If the file skates across the part, merely scratching it, the part is good. If the file cuts into the part is questionable. Most parts which have failed from overheating will show discoloration. However, be sure to check other parts if a heat failure is found. The heat treat may have been drawn out of other pieces, although they may not discolor or show other visible signs of damage. When replacing a burned gear, always replace the mating gears even if they seem undamaged. Not all heat failures occur immediately following a low oil condition. The heat treat can be drawn from the parts, yet the transmission may continue to operate for days before failing. The oil level could have been corrected before the failure is found, so don't rule out low oil level as the culprit. Problems can also appear on the clutching teeth of mainshaft gears. A new mainshaft gear has clutching teeth with straight sides and square corners. Since mainshaft gears mate with sliding clutches, the following observations apply to the clutching teeth of both. During the operation of a transmission, it is normal for the corners of clutching teeth to become slightly rounded. This normal wear will not affect the performance of the parts. However, chipped or severely rounded clutching teeth will help create a slip-out problem. This wear can be caused by improper clutching and shifting techniques. Parts as badly worn as this should be replaced. The clutch tooth faces can also wear from use until they are tapered rather than straight. Tapering contributes to slip-out, so replace such gears and clutches. Excessive vibration from the engine or driveline will speed up this tapering process. Check for causes of vibration if excessive tapering is found. Don't confuse tapering due to wear with parts machined with a back taper or helix angle on the clutching teeth. We machine this angle to draw the gears together and help prevent slip-out. Helix clutching parts are used in sets and cannot be mixed with parts having straight-sided clutching teeth. Check the Super Parts book to be sure you use the correct parts. And remember, if you replace a sliding clutch because of a clutching tooth problem, you should also replace its mating gear. Some mechanics replace gears they feel are defective because of marks left on the gears by manufacturing processes. The machining marks are normal and do not contribute to gear failures. Hob marks are formed during the initial cutting of gear teeth. Additional machining processes remove hob marks on tooth faces, but these marks will remain at the roots of the teeth even on gears with much wear. We machine the final tooth form by the shaving process. This leaves distinct diagonal marks on the face of the gear tooth. As the gear wears, these lines, commonly called shaving marks, slowly disappear. Sliding clutches are not shaved, so the hob marks will remain on the teeth. Some Fuller transmission gears are honed after heat treatment to improve the finish on the tooth faces. The honing process will remove some of the shaving marks, giving the gear a used look. The appearance will vary from teeth in which only a small portion appears polished to ones where the entire face is honed smooth. When too much torque or not enough reduction is imposed on transmission shafts, failures result in the form of twists or even fractures. Twisted main shafts will cause the sliding clutches to bind on the crooked shaft splines, resulting in hard or impossible shifting. As with gear teeth, shafts may also fracture as a result of shock or fatigue. Impact fractures may appear as either jagged or smooth at the brake surface, but both types lack beach marks. Fatigue fractures can usually be identified by the presence of beach marks. Some common causes of shaft twists and fractures are improper clutching techniques, starting in too high of a gear in either the main or auxiliary section, lugging, or a severe shock load to the driveline and transmission. During normal use, the clutch plate splines sometimes wear into the transmission input shaft splines, causing the clutch to stick during engagement and disengagement. Some conditions which can cause premature input shaft spline wear are excessive engine vibration, improper working angles, starting in too high a gear, and lack of a spring-dampened clutch. The indentations on this input shaft may look normal for a high-mileage vehicle, but if it is found at low mileage, it could indicate a misaligned clutch or flywheel housing, loose clutch housing cap screws, or improperly adjusted transmission rear supports. Synchronizers fail due to improper range shifting techniques, such as range shifting in neutral, downshifting at a high rate of speed, and vibrations to the rear of the transmission. There is a friction material on the surfaces of Fuller synchronizers which has greater wear resistance than bronze synchronizers. Over a period of time, not pre-selecting the range shift can cause damage to the synchronizer and mating parts. This damage results when the driver is not moving the range button until the lever is in the neutral position. All range shifts must be pre-selected. When the driver doesn't pre-select properly, torque is applied to the driveline before the speeds of the gear and sliding clutch are matched. The load of the vehicle may be driven by the friction surface of the synchronizer, causing the synchronizer surface to overheat and wear. The friction surface of the auxiliary drive gear can also overheat and score. Downshifting to low range at too high a road speed can also cause the synchronizer surface to overheat and score. When replacing a synchronizer, be sure to check the mating surfaces of the reduction gear and auxiliary drive gear for resultant damage. When replacing synchronizers, replace any bronze synchronizers with the new interchangeable friction surfaced synchronizers. Vibration to the rear of the transmission usually affects the synchronizers first. The damage can show in several ways. While undamaged synchronizer pins cannot be rotated by hand, vibration from the rear of the transmission may cause pins to break or come loose. Vibration to the rear of the transmission can also cause the synchronizer springs to wear into the blocker pins. In some cases, 2 or more of these symptoms of vibration will show up. After replacing the synchronizer, be sure to trace and correct the cause of the vibration. Some causes of vibration are unbalanced drive lines, improper driveline working angles, unbalanced wheels or brake drums, worn suspensions, drive axle bearing failures, drive line out of phase. Other symptoms indicating vibration to the rear of the transmission are repeated rear seal leakage, continual loosening of cap screws, brackets, and mountings, and vibrational noise which appears to come from the transmission. Generally, transmission bearings fail as a result of contamination or corrosion, overloading, misalignment, brinelling, and lack of or improper lubrication. Driving against one race with the resistance on the other can cause brinelling, since the force is directed through the balls or rollers. The same damage can result from driving on one side of the bearing, thus overloading at the impact area. Brinelled bearings will be noisy and will pit and fail prematurely. To prevent brinelling, always use flanged drivers which contact both the inner and outer race. Improper installation or removal techniques can also damage retainers, shields, or snap rings on the bearings. Bearings will fatigue after living out their expected life. This is normal after high mileage. Premature fatigue is generally caused by an improper re-sleeving of the transmission case bores in which the bores are machined egg-shaped or off-location. Out-of-round bores will squeeze the bearing races, causing an overload. Off-location bores will misalign the bearings, causing edge loading of the raceways. Never prick punch a bore to tighten the bearing fit. Bearing bores are sometimes re-sleeved because of fretting marks found around the outer bearing race. Often, the first assumption is that the bores are too large, allowing the bearing to spin. This is not the case. Fretting marks are bore marks which are picked up as the bearing race slowly turns during normal use of the transmission. Fuller transmission bearings are designed to fit tightly on the shaft and slightly tight to slightly loose in their bore. However, the bearings will not spin in the bore unless a metal chip or other form of contamination enters the bearing, preventing its balls or rollers from rotating. In that situation, the bearing and bore would be badly scored and burned. Contamination can enter the bearings from 2 sources: from improper handling of the bearings during repair, and from inside the transmission, such as metal chips resulting from clashed shifting. Avoid contamination during repair by keeping the bearings in their containers until ready for installation. Reused bearings should be thoroughly cleaned, oiled, and wrapped with a protective material until ready for use. As with gears, bearings can fail from insufficient lubrication. Failures from lack of lubrication are characterized by discoloration of the bearing parts, spalling of the raceway, and possible breakage of the retainers. Burning of the bearings and gear usually occurs together, so check out the bearings if burned gears are found. To prevent lubrication failures, follow the recommendations in the lubrication brochure Form 121. On Fuller transmissions, a bushing located inside the input shaft is used to support the front of the main shaft when in neutral. The bushing is designed with 35 to 45 thousandths of an inch clearance between itself and the main shaft journal. Using a bushing with a smaller inside diameter will cause slip-out and possible seizure of the main shaft. To assist you in diagnosing problems, a guideline is provided in the General Troubleshooting Guide for Fuller Transmissions, Form 102. The guideline lists the most likely causes for the most common complaints. Information for correcting the problem is also provided. Since noise is often a good indicator or warning signal of a problem, let's use it as an example. First, locate noise in the problem column and trace that line horizontally across the page. Above each numbered rectangle is a possible cause for the noise problem. Trace up all of the numbered boxes to locate all the listed possible causes. In this example, there are 9 things to check as highlighted. When tracing an actual problem, combine these hints with the information presented earlier in this program and some process of elimination, and you will save yourself much time. For example, if a noise complaint comes in, get a better description of it, or better yet, listen for yourself. Is it a thump, growl, whine, rattle, or other noise described earlier? Noise types will help tell you what type of failure to look for. Noise and vibration should also be identified as either constant or intermittent. Generally, a constant noise or vibration throughout the range of a particular gear position can be related to the transmission, axles, or bearings. In contrast, universal joint or propeller shaft noise or vibration is intermittent and present only at certain vehicle speed ranges. Does the noise appear only in low range? If so, the failure is probably in the auxiliary section, since all power passes through the auxiliary section reduction set in all low-range gear selections, but not in high range. Now, for example, let's say the noise appears in 1st and 6th speed gears only, in a 10-speed transmission. Then the problem is most likely with the 1st speed gear set, since it is used for both 1st and 6th speed ratios. Save time locating the defective part by tracing the origin of the noise. Eaton Truck Components regional offices are located throughout the U.S. and Canada to give you quick answers for those unusual problems. Their experienced personnel will be happy to assist you. Give them a call. To keep current on new information, plan to attend a service school at one of the Eaton Truck Components regional offices. Training sessions are given on a regular basis and provided free of charge. Write or call for a current schedule of classes and a detailed description of course content. Many types of literature are also available, such as service manuals, troubleshooting guides, and wall charts. Each has been designed to assist you in keeping your customers on the road. Along with your mechanical skill and experience, the information presented in this program will help you identify the cause of a transmission failure and assist in determining just when component replacement is necessary.